So the next lecture, what I'm doing, you do this. I'm delighted to introduce Professor Aneta Stefanovska from Lancaster University, and she's going to present on a time-resolved approach to image and signal analysis.
Thank you. Possibly I will be sitting because there are many slides that I need to run, so I apologize for not standing up because there is no remote controller. I hope you're okay with this. So thank you very much for the invitation. It's a very interesting opportunity for me here to share you started this, okay. I hope it's okay now. Yes. Oh, perfect. Okay, so thank you very much for the invitation. I kind of do not fit among you, and I kind of fit very much among you. I hope at the end you will decide whether I fit or not. The reason why is because I'm not coming so much from the imaging side. I'm coming from the signal side. And I have been trying myself not so much to do imaging, but to understand the basic principles of life. My background is in biocybernetics and theoretical physics. And I have been dealing with trying to understand the principle of the functioning of living systems for over 30 years. And I hope to have a chance to share with you what I have done. So whenever you image or measure, you end up with some kind of data. And what you can do with the data, you usually can either don't bother how much they are ordered in time and do all sorts of statistical analysis, like applying Bayesian rule, calculating probability density, obtaining various random variables. You can apply information theory, you can apply pattern recognition, you can apply artificial intelligence, machine learning, data mining, neural networks, whichever approaches. But if you order the data in time, you have dynamical systems signals. And then you apply theories for dynamical systems. And you analyze also behavior of the systems that generated the signals, which is kind of the goal of those like myself wishing to understand principles of living systems. So you try to search for cause and consequences or input and output in engineering sense. And in this way, one can have many opportunities to treat the signals as stochastic and treat them in probabilistic manner, or to take them possibly as deterministic and search for deterministic patterns. Here, even if you decided that there might be some determinism, you still have two possibilities: to think about the systems that generated the signals as being autonomous, meaning they do not depend on the external influences, or non-autonomous, meaning that you explicitly take into consideration that what you're measuring is not only the parameter you measured, but maybe also some external influence. And this is very often in living systems, because no matter how much microscopically we go, when we talk about function, we cannot take away either the couplings between systems or external influence. We cannot isolate as we are used in physics. In physics systems, you know well that you can isolate your system, and then you can measure, reproduce the measurement as many times as you wish and get a characterization of your system. If there is a case of non-autonomous systems, the influence may be changing, so the reproducibility of measurements may not be as you may expect. So once again, when trying to understand principles, one always think about structures of living systems, and the basic unit of structure, probably you would all agree, is the DNA. Fascinating molecule. Apparently, the amount of information stored in a single human by 2007 was about twice as much as all the information stored in every technological device on the earth. So this is about DNA, and this is about the fascination of a living structure. But there is another molecule that is very important. And this molecule, in my opinion, hasn't been considered sufficiently over the last decades. And this is ATP. ATP is producing energy. And this is the key of how to see living systems in terms of their functioning. Contrary to the cars outside that can put petrol and have energy, assuming it's continuum, our body produces or changes, or by chemical processes, it changes substances into energy continuously. And this change may not be always 100% continuous. Moreover, this change may not be always correct, or may be adaptable or something. Interesting enough, with this functional aspect of living system, it goes that we produce daily ATP of the amounts equivalent to our the weight of our human body. So this production may not always function well, and we never take this into account. When monitoring living systems, they are living because they can produce ATP, and we don't take this into account. How does this manifest? So with one of the methods that you are developing, this is fluorescence microscopy, one can see easily that the correspondent parameter to ATP production is fluctuating, or if you wish, oscillating in time. This is the time evolution of the recording made over some 1,600 seconds, which is quite substantial amount of time. And here you can see time frequency representation, and you can see that the frequency of these oscillations is not clock-like, it's not perfect. So is functioning of living system deterministic or random? Just to clarify, determinism is when events are determined completely by previously existing causes, and in physics we know this as cause and effect. The opposite of determinism is randomness. This is apparent lack of predictability in events. So the question is where we are with the living systems. Are we on the deterministic side or the random side? But before going on to think about, let us actually recall oscillations. In systems that are open loop, which means that you have some cause and some consequence, and there is no information backwards from the consequence to the cause, you don't have oscillations. But if you had some feedback, and nature, whenever you study, whatever you study, if you studied biologically clearly, you would have found out that there is signaling all over. Signaling means, biologically, signaling means that there is some feedback loop informing, don't go too far, because things may be wrong. And in this case, when we have a simple feedback loop, we can induce oscillations, but they can die. And when we have both positive and negative feedback loop, which is more often a scenario for living systems, because everything that is functioning in our body can be going up or down in the parameters. We have so-called self-sustained oscillations. Oscillations are continuous, they don't die. You don't produce them, they are there as natural manifestation of biological systems. So from these kind of scenarios, whichever of them, you do imaging or measurements, and then there are signals or time series or time-space data, if you wish, that I analyze. That's my kind of activity. So oscillations, now, how can we treat them? What is the problem? Sometimes it looks like that oscillations are mathematically very trivial. If they are clock-like, well, what an excitement is to see a sine function. Nothing. It's a frequency, an amplitude, and nothing more. So it looks like, why should we bother if we wanted to study oscillations? But yet, the functioning of every cell, we saw that ATP production is oscillatory. We will see in a moment that the heart is beating in an oscillatory manner. I mean, we don't need to see, I'm sure you know this well. But because they are interacting, they change, they mutually influence their frequencies. And we end up in a scenario which is mathematically and physically very difficult, contrary to simple sine or cosine functions for clock-like systems. And we can think of oscillation in almost every variable. For example, blood pressure, you well know that oscillates. Blood flow, if you measure it in whichever way, oscillates. All sorts of substances, concentrations that you can measure, oscillate. So it might not look conventional picture, but absolutely essential for realistic analysis and imaging. So just to illustrate what I mean, let us consider heart-lung interaction. Heart is usually represented by its electrical activity, and I'm sure you all are very familiar with so-called ECG. To measure lungs activity, you can put respiratory belt around the thorax, and you can measure the expansion of the thorax or due to the expansion of the thorax volume. So here we have ECG and here we have respiration. And here we have what is known as heart rate variability. This means instantaneous frequency, if you wish, of the heart, of the beating of the heart. And this is just, don't be, I mean, it's just indicating that we have occasional phase slips. So if I go over time, you can see that the heartbeat is changing. The frequency is changing because these ECGs are sometimes more close together and sometimes more apart together. And simultaneously, I'm recording respiration. And if I'm extracting the instantaneous heart frequency, I can see that actually the signal most of the time looks very much, it goes sometimes out of phase, but otherwise very much looks like the respiration. This means actually that the heart rate is modulated by respiration. So because of this modulation, the beating of the heart is no more clock-like. Okay? And if you think about periodic oscillations, what I call asymptotic approach means everything is in terms of cycle constant, and we can apply asymptotic approach. Asymptotic approach means whatever I've observed now is true forever. So time goes to infinity is the approach that we apply. And in this asymptotic approach, we have defined amplitude and phase for oscillations. we have defined also for a non-asymptotic approach, of course, every oscillation mainly is defined by amplitude and phase, and the amplitude can be, constant, or the amplitude can vary in asymptotic approach. But in reality, we also have other kind of changing oscillations, not only changing in amplitude, which are very much more used to think about. The changes, so this is modulation in the amplitude of oscillations, as well as phase to power is modulation of the amplitude. But we have so many cases in living systems when we have modulation of the frequency. For example, you can write down some kind of phase oscillators where the coupling is such that it influences the frequency. So obviously I'm introducing another term, coupling between the modulating and modulated oscillatory processes. And coupling functions describe the physical rule of how the interaction occurs. And it provides unified and systematic way, of describing mechanisms of coupling. But coupling is well known, especially in radio engineering, for long. We know about frequency modulation and amplitude modulation. Maybe we have forgotten why most of radio is frequency modulation, not amplitude modulation, although our mind is much more easily coping with amplitude changes. So frequency modulation has been shown, and that's why all the radio is on frequency modulation, to be much less prone to errors in transmission. So that's obviously a scenario that nature may have selected to have frequency modulation. But these results, please see this, results in non-constant frequency. And oscillations with non-constant frequencies are today very difficult to treat. I hope I will convince you that some of these difficulties is overcome, but not all. So I can ensure you that nature abandons with frequency modulation. I showed you that respiration modulates the frequency of the heartbeat. There are all sorts of other physiological processes that are in this relationship if you made some analysis. So we have to ask our question, and we need tools to analyze imperfect oscillations. So far, most of the cases with imperfect oscillations would end up in the basket of random dynamics, because I'll show you in a moment how Fourier transform, for example, immediately classifies them as noise and so on and so on. So we must have methods that take into account time variations. For example, wavelet transform, and I will argue that wavelets with Morlet, or what we have proposed log-normal wavelets, are probably the most appropriate if you wanted to have time frequency representation. In any case, the aim is to reconstruct the behavior of the system that generated these kind of signals. So as I mentioned, if we have this kind of modulation where the frequency changes over time, whichever, in this case, it's chirplet-like modulation, but it does not matter. If you did simple Fourier transform, you would have obtained a spectrum which is covered most of it. And this is how we usually classify randomness. So Fourier transform indeed links the time and frequency domain, but it does not show both at the same time. When we have Fourier transform, we can detect a single oscillatory component very easily. But the question of randomness is not well resolved. As I said, this kind of signal, if you did, for example, power spectrum density analysis, would for sure end up in the basket of random. But I can assure you the signal was generated by totally deterministic equation. So in Fourier transform, we have either time or frequency, but not both. And Fourier transform can be considered as an asymptotic approach because it requires infinite time and because it requires strictly periodic oscillations. So if we did Fourier transform, I didn't show you the equation, but I can tell you this is Fourier transform of something that has been simulated for the signal itself over almost 21 hours to ensure perfect frequency resolution, because I'm sure you are all familiar that frequency resolution is proportional to the length of observation. And in this case, it's sampled at 200 Hertz, but this information is, for the time being, it's not relevant. So what I want to say, this is a case, I hope you see, so here is frequency and here is kind of amplitude. A case where we see many, and one can count at least 93 clearly visible distinct peaks. There may be more peaks that are not so clearly visible on the scale shown. So one of my collaborators was pedantic enough to count 93, but maybe there are more. So we may easily wish to conclude that there are at least 93 distinct oscillatory processes resulting, producing this signal. But if we did time frequency analysis, and I'm showing you only 12 minutes of the signal, I'm just telling you that the Fourier transform I showed you before comes from something that has only two frequencies that are time varying. Only two frequencies, and this is what we have developed. We call it MODA, our toolbox. I'll tell you more in the end. So if we have only time or only frequency, we may end up with wrong conclusions, especially in case when we have frequency modulated oscillations. So asymptotic, by asymptotic, I mean approach when we assume time goes to infinity, right? Is often inappropriate. Applying analysis method based on time homogeneity assumption to systems where this is unrealistic will lead to very incomplete or even erroneous understanding. And I will now spend some time to explain that we need non-autonomicity. You may ask, what is non-autonomicity? It's when the system's evolution law is time varying. It's still deterministic, but time varying. And can result from time evolving environment, which influences usually thermodynamically open systems. That's what we are talking about. I don't have time to tell you more about definition of thermodynamically open systems, but it just in brief, systems that are not left alone, that cannot be isolated from the environment. And many systems are open, almost no living systems is isolated. And we have to think about them in the right way. So what are non-autonomous systems? Non-autonomous systems explicitly depend on time. So their changes over time are also time dependent. This means their parameters will be time dependent, their frequency will be time dependent. And conventionally, when I started dealing with this about 10 years ago, almost every good mathematician wanted to convince me that every non-autonomous system will be changed into autonomous in no time. Mathematically, no way. Only the simplest case. I can give you millions of cases where this cannot be done trivially or easily or at all. So we must treat them as non-autonomous. And what does it mean? I show you here another example. So this is 3 modes. They are interacting and modulating. Maybe just a brief summary of what I already told you. So these 3 modes, once again, even if I went with time windowed Fourier transform, yeah, which I'm doing it here now. Before it was just simple Fourier transform. This is short time Fourier transform. Because of the linear resolution Fourier transform has, we end up either being biased towards the fast ones or towards the slow ones, but we cannot be good for everything with with short time Fourier transform. Namely, you know that frequency resolution is 1 over the window length, and this is not linear relationship. So linear scale is distorting the reality immediately. If we did wavelet transform, we can, with optimal selection of frequency resolution, find out that again we have simple case of 3 time varying modes. I just wanted to say this one is also time varying, but the window that we have selected here is not long enough to reconstruct this. And I will try to convince you to the end. These systems must be defined for the time of observation, not generally. So what can we do actually? Why do we need all this? Let me show you a practical example, a real example. We conducted a study of treated hypertension some years ago with cardiologists involved. Treated hypertension means that all subjects that we measured were normal blood pressure, but they were taking medications. 5 minutes. Thank you. They were taking medications. So we measured respiration ECG, and using laser Doppler flowmetry, we measured microvascular flow. And we extracted information like these are the signals, ECG again, respiration, and very curly what is microvascular blood flow. I haven't spoken about ability now when we evolve in time and in frequency, the power or the amplitude of certain signal, we can follow or trace the phases by tracing their ridges. So this is how we ended up with these signals here by so-called ridge extraction. And we applied all sorts of methods because we have battery of tests. So we decomposed oscillations into contributing modes with ridges. We can take into account also high harmonics of time-varying systems or processes. We can calculate wavelet phase coherence, which is instantaneous over time. We can also extract interacting mechanism using bispectral or wavelet-based bispectral Bayesian inference that we developed. And not lastly, we also test every of these approaches by surrogate data testing. I don't have time to tell you what are the rigorous statistical measures when you go this way to evaluate the correctness of your conclusions. But my point is that applying this, we end up in finding out that treated hypertensives will not have restored one of the oscillatory, which is coming from myogenic function processes. So you can see age-treated hypertension compared to young or aged people do not have this oscillatory component. So I will skip this brief conclusion. For those of you who want to have more insight into this work on how we can see hypertension by applying non-autonomous approach and time-varying view of the frequencies, this is the paper. What I wanted to show you is, so this result that we obtained, we interpret as the endothelial function has not been restored in treated hypertension because the hypertensive drugs today are gauged to larger vessels, not smaller vessels where endothelium plays significant role. While with this approach, we can non-invasively measure the functioning of endothelium. And this functioning of endothelium turns out to be key for COVID. But I will discuss for those of you who are interested maybe later on. I don't have time. I just want to say that based on the approach that I only had a chance to glimpse you at, we developed many methods for time series analysis. And these methods are summarized in our multi-scale oscillatory dynamics analysis toolbox, which is available in MATLAB and in Python. And you, in addition to time frequency analysis, you have possibility for ridge extraction and filtering, wavelet phase coherence, wavelet-based spectral analysis, dynamical Bayesian inference. And there is very nice manual also for those of you. For the physics background of all I try to tell you now, almost rushing, we published recently Physics of Biological Oscillations book. There are several papers that are very informative for this topic. So to summarize, what did I want to tell you in this presentation? Do not insist on reproducibility of your measurements. I mean, when you do biological experiments, of course, when you are in laboratory, your equipment must work on phantoms perfectly well, must be giving reproducible results. But on living systems, you don't need to insist on reproducibility. This is similar to if you wanted to insist that the temperature in Glasgow, if you measured every hour, would be reproducible, or every 2 hours, or every day, or every year, whichever. No, this is similar to living systems. There is a wealth of information, even if the most noisy looking biological data. Don't throw it away. They often contain the dynamics of many coupled and frequency modulated clocks. Take time as a physical variable, not only as a mean of ordering your samples. Do not unnecessarily filter and smooth the time series that you obtain with measurement. The variability may bear relevant biological information. And the toolbox model offers a number of methods that are appropriate to signals resulting from functioning of coupled interacting clocks and oscillators. And I want to acknowledge all sorts of funding sources that have been making available this work over the last 15 years. Thank you very much for your attention, and of course a great thank to my many collaborators, too many to list them on the page. Thank you very much.
Thank you. I think we've got time for maybe one question.
For your software,
Moda.
is available on the website? Or?
Yes, it's a freely on. In my abstract, you have a link.
Okay.
It's freely available on GitHub. As I said, both in Python and in MATLAB versions. Okay.
Thank you very much.